Hi everyone, and welcome to this, which is the 8th of our webinars for 2016. And today's discussion is titled Better Assessment of Slabs in Buildings using LimitState SLAB. Just to introduce myself, my name is Tom Pritchard and I'm the host for today's session. I'll be passing you over to our first speaker shortly and also presenting the second practical segment after that's concluded. We do hope today that you'll come away with an overview of how you can apply our yield line analysis software LimitState SLAB to a range of building slab assessment problems, see how it can help you in both the design stage and to demonstrate that existing slabs have potential reserves of strength that you may not be aware of. The webinar is due to last around 45 minutes and will include at the end about 5 or 10 minutes for questions, which can be posted via the question functionality that should be present in the webinar interface that you have on your screens. We do try to answer as many of your questions as we can in the time available, but it's not always possible given the short time. So we are sorry if we don't get around to yours, but we will try and answer them after the webinar via email. Also, if you do have a technical question that might take some time to answer, you're also welcome to contact us outside of the webinar via info@limitstate.com, and we'll be happy to answer these in detail for you. So without further delay, I'd like to welcome you to our first speaker today, who is Professor Matthew Gilbert, and he'll be speaking about the methodology of automating the yield line method. And I'll now pass you over to him.
Thanks very much, Tom, and thanks very much, everyone, for joining us for the webinar today. Okay, just dive straight in. What's the webinar about? It's really about how we can take advantage of new technology that allows us to very rapidly evaluate the load carrying capacity of reinforced concrete slabs, whether they be existing slabs or whether they be new slabs. So the screen in front of you, you should be able to see a couple of yield line patterns on the left, which are quite conventional, the sort that you find in textbooks. On the right, we have a couple of yield line patterns which have been identified using LimitState SLAB, and what you can see is that they're more complex in form because of the irregular real-world nature of the structures in question. And the next slide shows those failure mechanisms brought to life through animation, so you can see exactly how those slabs are predicted to fail at the ultimate limit state. So what I'll be doing is telling you a little bit about how we've managed to automate the yield line method. Before I do so, I'll just say a few words about LimitState, the company. It's actually a spin-out company from the University of Sheffield. Recently celebrated our 10th anniversary, so we've basically been commercializing academic research for 10 years. Primary focus has been on providing engineers with powerful tools for the ultimate limit state. So taking advantage of optimization techniques which are not used in existing conventional software tools. Because it's a company rather than a part of the university, we're able to spend time making sure that the software tools are easy to use and also fully supported. 3 civil engineering tools available, one for masonry arch bridge analysis, that's LimitState Ring, one for geotechnical analysis, LimitState Geo, and the one of interest today is clearly LimitState SLAB for concrete slab analysis. These tools are now used quite widely around the world and also very popular in the UK. So big companies such as AECOM, Arup, Atkins, Balfour Beatty, etc. Using one or more of our software products. So just to look at our approach, when we started out, we felt that the collapse analysis tools that were available were kind of polarized. You had automated hand calculations on the one hand, may have been automated in a simple program or in an in-house spreadsheet, but problems with those tools are that very often they're a very simplified idealization of what you have in reality. So those tools are available, and at the other extreme we have advanced tools based on, for example, nonlinear finite elements and so forth. Very powerful. However, the downside is a lot of expertise required, a lot of time required typically, so not suitable for routine use. So we felt there's a large gap between these two types of tools, and we've been trying to fill that gap with mainstream tools based on numerical rigid plastic analysis, and applying that thinking to, for example, geotechnical problems, as you can see on the slide in front of you, to masonry problems, and also to reinforced concrete slab problems. So that's our approach, is provide mainstream tools which can be applied to practical problems in a quick and easy way. Okay, so in the context of this webinar, it's just worth having a quick recap on the yield line method. The term yield line was coined by Ingersleff almost a century ago. He did looked at rectangular slabs and identified that they fail through formation of yield lines. However, the main yield line method was actually developed by Johansson some years later, which was shown to be an upper bound plastic analysis method in the context of the theorems of plasticity. So when it was developed, the yield line method brought clear advantages. It was a very quick and direct, simple way of estimating the collapse load, and because you are analysing the collapse state directly and getting a good representation normally of the collapse load, it leads to economical designs or to realistic assessments of capacity in the case of existing slabs. Unfortunately, it stayed for the vast majority of its life a hand method, so that required the engineer to manually postulate a collapse mechanism, and unfortunately, if you chose the wrong mechanism, then you would overestimate the true collapse load. Sometimes there are cases where that overestimation could be quite significant. Other disadvantages is it's got to be borne in mind, it is quite a limited tool. It deals with flexural failure only, doesn't tell you anything about the propensity of a slab for shear failure, and doesn't provide any indication about deflections prior to collapse. Nevertheless, it's been found to be very, very useful. So, for example, Middleton and co-workers applied the technique to bridges and showed that many bridges which were deemed likely to not be capable of carrying a given loading actually could carry the required loading. And what that software did is it actually looked through a library of potential collapse mechanisms and worked out which of those mechanisms was critical and what the corresponding collapse load factor would be. The only problem is it required the critical mechanism for your particular slab that you're actually considering to be one of these, in this case 27 library mechanisms. There's always a worry that your particular slab might fail due to a different mechanism, and hence you would overestimate the collapse load of your slab. In terms of applying the yield line method to buildings, we can observe that the kind of technique that was applied to bridges is perhaps less suitable for buildings, because we often have quite irregular shapes. However, if we can apply it, then very, very useful for a variety of different purposes, either in new design or, as indicated here, in a rehabilitation project where we can, for example, demonstrate an existing slab has sufficient strength for the new purpose of the building. If that's the case, clearly we can avoid the need for expensive strengthening work. And in the case of an existing building, serviceability might be an issue, but if it is, when we can often actually do physical load tests. We can actually bring in containers carrying water, pump the water up, and actually exert load and measure the deflections. Okay, so I mentioned early on that we'd automated the yield line method. So how did we do that? Well, we actually used something called discontinuity layout optimization, or DLO for short. It's a very quick and direct means of identifying the critical yield line pattern. We published details of this method in a prestigious journal a couple of years ago, the Proceedings of the Royal Society. And to explain it, I've got a few diagrams which I'll show at the bottom of the screen. So if you start with for example, a square slab with fixed supports as an example, the first step in DLO is to populate that slab with nodes. We then connect each node to every other node with a potential yield line, and then we use optimization to find the minimum energy solution. And it turns out this boils down to a simple linear optimization problem. So we can solve problems very reliably and also very rapidly. So what that means is we can potentially put many nodes in across our slab, and so we can get very accurate solutions. So for example, for a fixed square slab problem, that's the middle one of these three slabs you can see on screen, we're able to get within 0.01% of the known analytical solution for this particular problem. And another thing to point out is that we can identify automatically features such as corner fans or corner levers very, very readily. So there's no need to manually suggest any features of the failure mechanism. The true failure mechanism will be identified automatically. Also, key thing is we can now move beyond the textbook solutions to more realistic geometries. So here we have an irregular slab with a hole that's been considered in the academic literature in the past. When we apply LimitState SLAB to this problem, we get a solution which is better, i.e. a lower load factor than has been obtained using any other method in the literature. Moving to another literature example, but definitely a real-world example. It's actually a slab in this London apartment block. You can see perhaps that the perimeter has got lots of curves in it, so the resulting slab is quite complex in terms of its geometry. And the other thing to point out is we have these blade columns oriented around the area of the slab to provide supports. Now this particular slab was actually used in a guide prepared by the Concrete Centre in the UK about 10 years ago, and the guide proposed the use of the yield line method to design this slab. Now what that required was manual consideration of a variety of different yield line patterns. So you can see pattern 1, 2, 3, 4, 7, 8, 9, 10, etc. on the right-hand diagram. You can also see the yield line pattern identified to be critical. It's a sort of a folding hinge type mechanism. You can see on the left there. When we enter details of the geometry into the slab, we could get a solution pretty much instantly. So whereas by hand this was a very laborious process to find the critical mechanism, using the software we could get the mechanism very, very quickly. And you can see actually the folding plate mechanism that was identified to be critical in the concrete center guide is actually largely found to be critical here. It's just a little bit more complicated. We've got the extent of the mechanism slightly greater than is indicated by hand. So hopefully this gives you an idea about how the approach works and how it can be applied in practice. But to give you a sort of hands-on view of a software, I'm going to hand you back now to Tom, who will talk you through application of the software to a series of examples.
Thanks, Matthew. And as Matthew said, what I'm going to do now is just open up LimitState Slab and go through a couple of examples, one relatively complex and one hopefully a little bit quicker, that will show you just how you can put in sort of loading and assess slabs using the software. So the first one we're going to look at is looking at an existing multi-storey office building which is undergoing some repurposing work, so sort of a typical example of it on the right-hand side here. And the first floor needs to take some props while work is being carried out on the floor above, and these props are putting a combination of point and line loading on this floor, and we want to see whether or not the slab can carry this proposed loading from the props at the ultimate limit state. And there's been some opening at works which have provided details of the current slab and beam reinforcement schedules. So what I'll do is I'll open the software, and first thing to say is there are a variety of different ways that you can introduce the geometry of your problem into the software. I'm going to use a DXF import today, but you can also use a wizard system that's built in, or you can draw things by hand as well. But what I'm going to do is just go to import a geometry and open it up. So it's something that we've already specified as a DXF file. You can click OK, and you can see here that we've got our slab as it stands, and what happens with the DXF is that closed loops of lines get interpreted as solids that then the software allows you to be able to select. So we have our slab geometry in there already. The next thing we need to do is actually apply some what we call structural definitions to each of the different areas within the geometry. So what we need to do now is actually make them. So if I go to the left hand side here, you can see we have a structural definition explorer with some built-in structural definitions, but we want to actually be able to generate our own. So I'll click on new, and we get this dialog here, and what we're going to say is we're going to call the first one slab, and we'll give it a color, sort of a light grey color maybe, so something like that. And all we need to enter are the bending moment capacities in the two directions for hogging and sagging. So if we look at something like this for our slab, in this case what we're going to look at is an NP of 151 kilonewton meters per meter for both top and bottom in both directions. And in this case our reinforcement is going to be at regular 90-degree angles to each other, so on a proper grid system. Alternatively, if you found that you had a reinforcement pattern that wasn't with the elements at 90 degrees to each other, you can change the angles here accordingly. Also need to specify the thickness and the unit weight of the slab, so we're going to put it in. So our slab is 0.7 meters thick, and the unit weight is going to be 24 kilonewtons per meter cubed. Basically that means that when we apply the self weight of our slab, then that can be taken into consideration using these figures here. So we have our slab has been generated. You can see here now, if I click on it in the structural definitions on the right hand side in the property editor, all of those properties that we've just specified are available. And what we can do is just drag and drop our slab structural definition onto the problem there. Similarly, what we might want to do is also make one that is the beam. So I'm going to make the beam, make it a slightly different color just so that we can differentiate it. And in this case, obviously the beam is going to have higher bending moment capacity in one direction, so we can have our values here, and we've already worked it out. Again, similar top and bottom reinforcement. And in the second direction, we'll just go to 151 as before. Again, 90-degree angles between the reinforcing elements, and our beam is going to be the same thickness as the slab and the unit weight of 24. And once we define that, we can then drop it onto the geometry like that. So we have our geometry, we also have our structural definitions on there now. So the next thing we need to do is provide some boundary conditions. So first thing we want to do, we have a combination of columns, simple and fixed supports in this particular case. What I'll do is this square here is actually a column, so I'm going to delete the solid out of the middle of it. Use the rectangle select, just select all the 4 boundaries around the edges, and in the property editor on the right hand side here I can just choose external boundaries and select the support type that we want to actually apply on here. In this case it's a column that's going through the floor, and I want to apply a fixed boundary around the edges. Similarly, in the bottom left hand corner here we've got another column, but this time it's one that we want to actually provide a simple support to. And again, all you need to do is select those edges and apply them using the property editor on the right hand side here. And then the last 2 we've got is along the bottom edge here. What I want to do is have that as a fixed boundary, and then along the right hand side here, again specify that as simple. You can also have, if you see in the drop down here, partially fixed edges, and also if support liftoff is something that is likely to occur, you can also set that to true for the particular boundaries that you're looking at. In this case we're not going to do that, but it is something that is an option. So we've very quickly here built up the geometry, the structural definitions for each of the areas, and the boundary conditions. So the last thing we want to be doing now is actually applying the loading to this particular model. And in our case what we've got is, from the props, like I said, a combination of line and point loading. There is also going to be some dead weight from the slab itself and some other construction and service pressure loads that we want to apply, and all of that is dealt with by opening what we call the load case manager here. So this is where we apply different loads to different areas within the geometry, and also specify the partial safety factors that we might be applying. So in this case what we want to do is first set up a series of different loads that are representative of the different things within our system. So the point loads, the line loads, which are the from the props, things like that. So I'll just do an example of each, and in the best children's TV tradition I will open up the one I made earlier afterwards. So for a pressure load, all we need to do is add. You can see here it says it's pressure load. What we're going to do is change that to be services, and we know that our services in this case impart a pressure load of 0.27 kilonewtons per meter squared, and that they are a permanent loading. Similarly, we can add another one which would be construction loading, and in this case it would be 1.65 kilonewtons per meter squared, and we can set that to be variable, and so on if you had other pressure loads that you wanted to apply. Similarly, the next line down here we have line loading, and I want to make some for our props. So if I have prop type 1, and that can be applying a line load of 18.5 kilonewtons per meter, again we'll make that variable. And second prop type, prop 2, is a larger force at 45 kilonewtons per meter, but again variable. And similarly, in this case point loads, we have a few. I'm just going to make one. So if we have a dead load from the column in the corner, and at that dead load we're going to say is 800 kilonewtons, and because it's a dead load we're going to say that that's permanent, and we can apply that afterwards. So what we've done is we've applied a series of different or defined a series of different loads in our loads database, and then we can now pick from those when we're setting up our load cases in the load case manager. So the thing we would do then is go down this list here. So we have self-weight loads, and we click on that, and then just click change, select all of them because we want the self-weight from all of the solids in the problem to be applied. Click OK, and as I said previously, the software will now know what the thickness and the unit weight of all of these different solids is, and it will apply the self-weight accordingly. So second off, we want to apply some pressure loads. So we've defined a couple. So for services, and again, as before with the self-weight, we just click on this change and select the zones that we wish to apply that to. So do that, click OK, and we can see here the services are then applied in these positions. And we can go down. Secondly, we can look at line loads. So for our prop 1, all we need to do is click change, and what the software allows us to do is, if we want to zoom in, we can select a line that we want to apply our prop 1 line load over. If I click OK and display that, you can see in green here, that's where our line load is now going to be applied once we solve the problem. And for our props, we may want to have a series of them going along the line of this beam, and indeed that's what will happen shortly, but I won't go through doing all of them, but you can imagine how you would set them all up. And then lastly, point loads. It's very similar to the way in which you would apply line load. So we go, okay, here's our column, and I want to set the position of that, and our column is coming in to our beam to location on the left hand side here, which we can see there. Now we selected it, so if I click OK, you can see there that there is a pink dot with a cross in it that is signifying the downwards force from our column at that location. So we can go through and we can apply these loads and build up the problem as it is in real life. And I think at this point it's probably prudent of me to actually just open the file as we've made it earlier. So here's our problem again, but this time now, if I turn on the loading, actually I've opened the wrong one, apologies. That's better. So if I turn on the loading here, you can see that the line loading has been specified, and we have point loads for the column, and also in certain positions some reaction forces from the props. So we have everything now that we need to actually solve the problem. We have our geometry, we have our loading, we have our material types, and we also have the loading there. So the last thing we want to do is to specify the partial safety factors, and you can see in our load case manager how we're able to set the action type as being unfavorable and neutral, and similarly in the loads database we can say whether load types are variable or permanent or even accidental if we wanted them to be like that. And then by specifying in our partial safety factors the factors that we want to apply to each type of loading, we can then solve our problem and determine what the strength of our slab is going to be. So here we've got a ULS partial safety factor set, so 1.4 permanent, 1.6, etc. We're not going to factor the strength of the materials, we're just going to keep that as 1. And you can see here actually we've got all these different loads on it. If I click OK, and now what I do is just click the solve button. Actually on the right hand side here, Matthew mentioned about the assignment of sort of nodes to the problem in order to be the endpoints of potential yield lines. Our nodal density in this case is what we call fine. We have a sort of range of built-in ones going from coarse all the way up to custom if you want to put in lots of nodes, but in this case we're having 1,000 nodes in the problem, which is a fine resolution, and that should give us a good representation of the critical yield line pattern and also the associated what we call adequacy factor for the problem. So you can see now I've clicked solve and it's going through and it's highlighted now the critical failure mechanism, and it's basically, if I actually animate it, what we can see is the sort of corner levering off at the end of this beam here, and what we can do is just move that backwards and forwards so we can see how the failure mechanism is actually moving about. We can also see at the bottom here, numerically, we've got the adequacy factor on the applied loads is 1.2, which means because we have actually applied our partial safety factors already, that we're actually just looking for that value to be 1 or above in order to signify for that particular problem, for those partial safety factors, that we have the slab can carry the applied loading. So in this case, we'd be happy that the slab would be able to carry the applied prop loading and would therefore get on with doing the work as it stands. One of the things that you can also do, as well as animate the solution and see this numerical output, is get a report. So I'm just going to turn all those off. You can see if I click on report, it asks you which sections you would like to include in that report, so you can have a summary, see the geometry of the problem, all the materials, etc. If I click OK, then you see we get a nice report with all the data in it that we want, and we can then save that out for showing to the client or using ourselves later on. So that's very quickly gone through setting up and solving a problem with some static prop loading, but one of the other things you might want to do is potentially look at cases where you are wanting to bring across some plant onto your problem. So got an example here, which is a relatively thin slab which is supported along two edges, and say for instance the contractors want to take the plant vehicle up to the right hand side of it. There's a superimposed loading on that slab, and what we want to find out is, can the slab carry that proposed loading to the ultimate limit state. Again, what we've got is a vehicle here with some set wheel spacings, and we know that the load applied through each wheel is 11 kilonewtons. We've got the geometry of the problem, which we could draw in ourselves or import via DXF. So what I'll do now is I'll just close this problem and open a new one. So in this case, what you can see is we've already got the geometry of the slab in there. Like I say, again, for something like this, if you put on the grid, you could draw that in very easily by hand and apply the boundary conditions, or you could import it from DXF or whatever. We have our slab, and we can see that the MP values are, again, similar in both directions, but quite a lot lower than they were in the previous example, so 78 kilonewton meters per meter for both directions, and lightly reinforced on the top side. So in this case, what we want to do is actually look at moving a vehicle across this slab to see what the effect is of it approaching the right hand side. Again, everything that we want to be doing is controlled via the load case manager here, and if we look in our loads database, what I've already done previous to this is set up our superimposed loading, and also what we're going to do is represent our vehicle loading by a series of 4 point loads, each of which is imparting an 11 kilonewton load onto the slab. So if I click OK and go back into the load case manager, what you can see here is, again, as in the previous example, we've already set up our self-weight loading of that slab to be applied. We have pressure loading from this superimposed loading that we've already specified, and we have these 4 point loads, one of which represents each of the wheels. So if I click OK there and just view the system as it stands, you can see here we have the 4 point loads, which are representative of the wheel loading on the left hand side, and what we want to do is just move it in a line across to the right. So if I go back to the load case manager and have a look at this, all I want to do is say, okay, I've got my superimposed load and my 4 point loads for the wheels, and what I want to do is copy those across the slab. So I already know that this slab is sort of 6 or 7 meters wide, and I want to move my vehicle just horizontally across it. So my offset for each of the cases is just going to be 1 meter in the X direction, 0 meters in the Y direction, and I want 6 copies of it. So if I click OK there, I'll get a warning that says that the self-weight and pressure loads don't offset, because obviously you don't want those to be dissociated from the solid slab areas. So that's fine, so I click OK. Again, we've already set up our ULS partial safety factors. I can click OK there, and now you'll see here in the viewer window that we've got 7 load cases as opposed to the 1 that we had previously, and I can either use the up and down arrows in the scroll box at the top, or I can click between the tabs at the bottom here, and you can see that those 4-point loads are moving across until such a point where the front ones have actually come off the edge. So load case 7, I guess, is a slightly unrealistic load case, but it sort of bookends the problem. So we've got loads off on the left on load case 1, loads off on the right on load case 7. So now what we want to do, I'm going to leave it on a coarse nodal density for this one, just so that it solves a little bit quicker. If I click solve here, you can see that what's happening is the software going through each of these load cases in turn and working out the critical failure mechanism and the associated adequacy factor for each of those cases. And once it gets to the end, it looks through each of the load cases that it's gone through and says, okay, which one is the critical out of all of these? And in our case here, it's load case 6, which if I just put on the display of the wheels, you can see here, the vehicle is on the slab with wheels close to the right hand side there. Again, I can animate that solution and rotate it around so we get a better look at it. So we can see it's basically the edge of the slab failing. For other load cases, it's a more sort of traditional centerfold, and some of them are even a bit of a combination of the two. But we can see from that we've identified whereabouts, in this case, the critical loading is applied, and also seen that the adequacy factor is about 3.6. And again, because we've already applied our partial safety factors, we know that that's okay for this particular problem then. So that's it for the 2 demonstrations. What I do now is just sum up. So what we've seen today is that the yield line method provides a powerful means of analysing the ultimate collapse limit state. However, the lack of general computer-based implementation in recent years has limited usage, and LimitState SLAB in some way addresses this. For buildings, LimitState SLAB can be used either at the design stage or, as we've seen here, to show that an existing slab has additional reserves of strength. So if you're doing repurposing works, things like that, you can tell whether or not it's okay. So we're just going to have a look and see if there are any questions that anybody has. So if you would like to ask any via the thing, then we do it, and I'll pass you over to Matthew whilst that's happening.
Thanks, Tom. Okay, I'm just looking at the list of questions here. So if you just enter into your comments box, you can ask a question directly. I've just got one about skew reinforcement. How do we specify skew reinforcement? If we go back into the new structural definition dialog, then all we need to do to define skew reinforcement is actually just change the angle between the 2 different reinforcement directions to be different to 90 degrees. So that's the way of achieving that. Question about liftoff. What's meant by liftoff? Probably the easiest thing to do is probably to quickly just start a new example If we start with a simple square slab example, using the wizard, which we haven't shown, if I solve it with the default properties, then we have the failure mechanism that you can see here. If I change the supports to be simple initially, then we'll get something it's a little bit simpler, but very familiar. And what I'm going to do now is change that again to allow liftoff, because although this is simple support, is actually restricting the vertical movement of the slab. And so with liftoff, we will see that we'll actually get a different failure mechanism. And if I click the animate button, I will actually get sections of the slab actually lifting off from the support. In terms of the collapse load, I didn't dwell on what the loads and the moment capacity was, but what we had an inadequacy factor of 1.5, which is reduced down now to 1.38. So you can see that if you haven't got that vertical restraint, then clearly there is a penalty. Okay, looks like there's no more questions for now. So what I'll do is I'll just hand you back to Tom, who will just wrap things up.
Thanks, Matthew, and thanks to everyone for listening today. We do hope you found the webinar informative, and as mentioned at the start, if the presentations raised any questions that we haven't answered here today, please get in touch via telephone or info@LimitState.com, and we'll be very happy to speak to you. LimitState Slab is available to download or purchase now from our website, which is www.LimitState.com. We'll be in touch with everybody over the next few days just to get some feedback, find out if you have any further questions, and see whether you think LimitState Slab will be useful to you. We'll also send out a link to watch the webinar again, which you can use yourself, or if you want to pass it over to any colleagues who might also be interested to see it. Obviously, like I say, we'll send you a link once it's available online. Lastly, please look out for our other webinars that will deal with LimitState Slab and our other software products, which Matthew touched on at the beginning of his presentation. We'll be sending out event notifications via email in advance of all of these, and they'll also be posted on our website at www.LimitState.com/webinars. So finally, I'd just like to say thank you to all for listening, and I hope you can join us again for one of the future sessions. Goodbye.